All right, good morning, everyone. So as I just told Omar, I had about a half hour to an hour sleep last night. So if I kind of stop randomly talking and just stand here for a little bit, because I fell asleep while standing up to throw something. Should be fantastic. So anyways, just to remind you what we talked about yesterday to get your covenant ball shot up there. So we talked about current density. So again, we said current density is, at least magnitude-wise, equal to the current per unit area. So this is the microscopic version of current. So what this thing is saying then is that this is looking at how the charged particles are moving from position to position within inside of some sort of electrical element. Primarily wires, but in this case, again, it's on what the profile looks like, which means that we can find the current then from this current density by then simply averaging over the current density over the entire cross-sectional area of this particular electrical element, or our wire in this case. But again, for our purposes, we're always going to be looking at a wire, so this is going to be a cylinder, so we know the cross-sectional area is simply going to be, or at least the differential cross-sectional area is going to be 2 pi r dr. And J and dr, or dA point in the same direction, which means that the dot product portion goes away. This is going to be just simply 2 pi integral of J, which again is a function of R, integrated with R dr. We also talked about quickly Ohm's law. Ohm's law says that potential across this electrical element is then simply equal to the current times the resistance. So this is Ohm's law. So great. So as we talked about, again, basically our mental picture is this. So again, we have our battery that's applying potential difference. So we have potential difference across this electrical element. The battery is creating electric field, trying to accelerate these guys then through the electrical elements. But as my charged particles are trying to be accelerated through, they're hitting the atoms inside of the electrical elements, i.e. the resistor in this case, causing them to then accelerate, slow down, accelerate, change direction, slow down, speed up, slow down, speed up. So that if I average then over the entire length of this wire or over a large time duration, what we said is that what happens then is that these charged particles effectively move across this object with a constant velocity. Okay, so even though from moment to moment to moment to moment, the velocity is different, but again, over a long enough duration, i.e. the length of this object, and over a long enough time period, it has an average velocity, which is what we call the drift velocity. So first thing we're going to look at today then is, what is this drift velocity? And then how does it actually relate to the current density, and how does it relate to the current? Right? So again, here's our picture. This guy's trying to be accelerated through here by the electric field, moving like Planck through this entire thing until eventually it comes out to the other side. And again, if I average what this thing is doing over a long enough distance or a long enough time, again, this thing moves with a pretty much a steady type velocity. So more or less a steady type velocity, where that velocity is what we call the drift velocity. So what we want to know then is, again, what is this drift velocity, and then how does it actually relate to the current density as well as the current? So let's say we're going to assume that in this case, our current density is constant throughout the entirety of the wire, just to make it a little bit easier. So in this case, all that means is from position, 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 the amount of charged particles flowing through is the same. So again, we're going to assume that J is constant in this case. So here, let's say here is my single charged particle, but I'm going to assume that, again, since its profile is exactly the same everywhere through, I have kind of this whole entire cross-sectional area is full of these charged particles. And they're all moving in this direction, it's the drift velocity, because it's moving in exactly the same direction as the current density, in this case, since we know Q is positive. So now, what happens then is if I look over a time frame of, say, delta t, so let's look over this as the time frame of delta t, what's going to happen is this charged particle is going to move from this location to, say, this location here, still moving in this direction with the drift velocity vd. What happens then is I'm going to sweep out this particular area here. Or actually this volume here. So what happens is, as of this time frame of delta t, this charged particle moves this amount of length of L here, which then sweeps out this particular volume here, because again, this thing has some sort of cross-sectional area A. Cross-sectional area A here. So first things first, I know that this thing is, again, moving with a constant drift velocity, which means there is no acceleration. which means that I can rewrite the length here in terms of the second kinematic equation, which says that the position then is equal to the initial position, which I call 0, plus the velocity times the time, plus 1/2 the acceleration times the time squared. But since the acceleration is equal to 0, this is then simply going to be equal to the drift velocity times the change amount of time. So what? So here then, what I can say, well, is the volume which is contained inside of here, my entire volume, is then going to be equal then to the cross-sectional area times the length at which this electron or this charged particle has moved from the one side to the other side. But we now know L is the same thing as V times delta T, so I can rewrite then the volume as simply the area times this drift velocity, in this case the magnitude of the drift velocity, times my change in time of delta T. Okay? What's up there?
What's the inequality of the Q?
Oh, it just means that we're looking at positive charge particles. So that's why they're moving in the direction, which is the same direction as the drift velocity. Now, in this case, what we can then say is that what? The total amount of charge, which moved from this point to this point here, so delta Q, which is then equal to the total amount of charge. Delta Q then is going to be equal then to what? The charge of the charge carrier times then the number of charge carriers that we have. So capital N here is equal to the number of charge carriers. Now, to do this, we're going to define a new variable. So let's call our new variable little n, which is then equal to, so it's got it equal to, so this is equal to, so this is the number of charge carriers per unit volume. So this is what's known as the number density. So let's define this new quantity, little n. So this is just simply equal to the number of charge carriers per unit volume. So since I'm looking at a number that is unitless, but the volume has that units of 1 over meter cubed, so the units of this guy then is equal to 1 over meter cubed, or meters to the -3rd power. So another way I can then write my change in charge then, or the total amount of charge, is going to be equal to then the total number of charge carriers, times then the charge density, times the volume which is then swept out. So this is another way I could rewrite this. Now, from our previous slide, we said the volume then is simply equal to the cross-sectional area times the drift velocity times the change in charge, or sorry, change in time. So this is finally going to become the charge of the charge carrier times the number density times the cross-sectional area times then the drift velocity times the change in time. So basically, all this thing says then is that the total number of charged particles, which have been contained inside of this volume here, is then equal to the charge of each one of these charge carriers times the number density, which again is the total number of charges per unit volume, times that volume which is contained inside of that volume that we're looking at, which is then simply equal to the cross-sectional area times the drift velocity times the change in time. Now from here, we know that the current is equal to the change in charge divided by the change in time, which means the current then is equal to the charge of the charge carrier times the number density times the cross-sectional area times the drift velocity. So this is actually the current. So the current inside the wire is then the charge times the number density times then the area times the drift velocity, which means that my current density, at least the magnitude of the current density, then is going to be equal to the current per unit area, which is then going to be equal to the charge of the charge carrier times then the number density times then the drift velocity. Which means if I wrote this in a vectorial form, this then tells me that the current density is then equal to the charge times the number density times the drift velocity. Or the drift velocity is written as a vector. So what does this thing say? So as we mentioned basically yesterday, I think it was, when I was talking about current, what I said was you can think about current as basically the average velocity at which the charged particles are moving through these circuit elements. That's what this thing is saying. So this is saying that the current is then related directly to the average velocity at which these guys are moving through. Which means, again, we can think about the current as simply being the average velocity of these charged particles moving. This one then says, well, the current density is directly related to the drift velocity, meaning that what? These two things are going to point in the same direction. If it's a positive charge. If it's a negative charge, these two things actually point in the opposite direction. But the current density will always point in the same direction, because if I had a negative charge, I'd pick up a negative sign here, which means this would be pointing with a negative sign. The velocity then would be in the opposite direction, making the current density the same at all times. So whether I was looking at, if I go back to my picture, whether if I was looking at a positive charge particle or a negative charge particle, the current density will always be in this direction. But the drift velocity will either be in the same direction as the current density if I'm dealing with positive charge particles, but if I have negative charge particles, the drift velocity would be actually in the opposite direction. Because the current density has to stay within the same direction at all times. Yeah, that goes back to what we talked about Benjamin Franklin, which says that we always pretend it's positive charge particles which are moving, where in reality it's actually negative charge particles which are moving in the opposite direction. But they both maintain the fact that the current density always points in the same direction. Turns out, we're going to show in a little bit, it actually points in the direction of the electric field. So the current density always is in the same direction as the electric field, but the direction of the drift velocity is either in the direction of the current density or opposite the direction, depending on the sign of the charge. Okay? So let's do an example. So this example says that near the Earth, the density of protons in a solar wind, which is a stream of particles from the sun, is 8.7 protons per centimeter cubed. So this is my number density. So in this case, let's write that down. So here we know that our number density, so in our example, our number density then is equal to 8.7 per centimeter cubed. So this is my number density. And it says that they're moving at a speed of 470 kilometers per second. So what's happening here is, here's the Earth. Here's the sun way out here. Everybody know what a solar wind is? We'll talk more about this in a little while, but basically what happens is the sun has magnetic fields, where the magnetic field lines will actually eventually burst out through the sun itself and then come back in. This is actually what the spots are that are on the sun. So if you ever look at those dots that are on the sun, the solar dots there, it's actually where the sun's magnetic field is bursting from the surface of the sun and then going back into the surface of the sun. This is what's known as a promenade. What eventually happens is that this promenade becomes so big, what will eventually happen is it'll actually rip apart. When it rips apart, i.e. it breaks this magnetic field, so what happens then is the magnetic field gets cut, all the charged particles that are basically being pulled through by this magnetic field get then sent out in all possible directions, where some of them are going to be sent towards the Earth. This is what we call solar winds. So when this guy breaks here, this promenade breaks, it then sends charged particles, all kinds of different stuff, and in this case, we're going to pretend that they're protons. So in this case, we have protons, which are then moving with a drift velocity, which was equal to, what was it, 470 kilometers per second. So this is what we call solar wind. So basically, a solar wind is just a whole bunch of crap which is sent to us from the sun, which is full of basically charged particles. Now, what happens then is the Earth actually also has its own magnetic field. And it's a good thing we did, because as we'll discuss here in just a second from this problem, the Earth would be fried all the time from solar winds if we didn't have the Earth's magnetic field. So basically, the Earth's magnetic field shields the Earth from these solar winds, so the solar winds don't actually cross the surface of the Earth, which then would fry the surface of the Earth, basically. So this is a good thing. But anyways, so this is what solar wind does. So this is our problem here. So again, we have number density of 8.7 protons per centimeter cubed moving at 470 kilometers per second. And we want to know is what is the current density of these protons? That's part A. And then part B, we want to know if the Earth's magnetic field did not deflect the particles, meaning that all the solar wind went across the surface of the Earth, what then is the total current the Earth would receive from these charged particles? So let's discuss that. So part A, we want to know what is the current density. So let's say we want to know what is the magnitude of the current density. Well, we now know that the current density is equal to the charge of the charge carrier times the number density times simply the magnitude of the drift velocity. In this case, we're dealing with protons, so what kind of charge does the proton have? Positive fundamental charge, so it's going to be little e times the number density times the magnitude of the drift velocity. So here we know little e is the same thing as what, 4.602 times 10 to the minus 19. We know n, which we have to put into meters. We know b, which we also have to put into meters. But we do that, plug in all our numbers, what we find is this works out to be 6.54 times 10 to the minus 7 amps per meter squared. So this is our current density. Doing okay so far? Part B then says, okay, so what is the current? So what's the current? So we also now know that the current is simply equal to the charge times the number density times the drift velocity times the area, which is the same thing then as simply the magnitude of the cross-section or of the current density times the area. Because again, we're assuming that J is constant in this case. So we pull it outside of the integral, which means we would just get then the integral, or this is then the cross-sectional area. So the question then is, if I have a sphere, which is what the Earth is, and I'm shining light then onto the sphere, what is the effective shape of effective cross-sectional area that the solar wind is seeing when it's then impinging then onto the Earth? So what is the cross-sectional area? Circle. Just a circle, right? I'm kind of holding myself here so you can kind of see that. So it's blocking the light, but it's only creating a circle out here, which means that the cross-sectional area, what I care about, is simply the cross-sectional area of the Earth, which is that of a circle. So my cross-sectional area then is simply going to be equal to pi times the radius of the Earth squared. So in this case, my current then is going to be my current density times then pi times RE squared. Look up the radius of the Earth, which I don't remember offhand what it was, and I didn't write it down. I wasn't smart enough to do that. But basically what you would find is that this works out to be about 8.34 times 10 to the 7th amps. Now, to put this in context for you, what type of currents do you need to kill a person? Because remember, what kills a person is not voltage, it's actually current. So different people can touch different voltages because each different person has a different amount of resistance to them. So what is the type of current that you would need to actually kill a person? It is. There's more in there. Well, like AC current? Any current, in this case, it's direct current, but AC current's a little bit different. It's actually 100 amps. All you need is 100 amps through a person's heart to actually stop their heart and kill them. So if we only need 100 amps to kill us, this is what? 5 orders of magnitude greater than that. So if the solar winds hit the surface of the Earth, where we had no magnetic field to actually shield the Earth from the solar winds, this would simply kill every single person on the face of this planet, as well as every animal, as well as basically fry the surface of the planet. It would be a barren wasteland without the Earth's magnetic field.
I think I could take it.
What's that?
I think I could take it.
You can take it. got good skin. There we go. So good. So this is just a huge amount of current. This would basically wipe out everything which is on the surface, on the surface of the Earth. Okay. Let's do another example. Good. So this says we have a copper wire, where that copper wire has a 3.2 millimeter in diameter width to it, and then carries a current of 5 amps. We want to determine the current density in the wire, the drift velocity of the free electrons which are allowed to move within inside of the wire, and then what is the Rms velocity of the electrons which are moving inside of the wire if we assume that it's an ideal gas at 20 degrees Celsius. Good. So let's talk about all this. Let's look at it. So here's our next example. So here's my wire. Great. This wire has a diameter D, and we know it's carrying your current, where that current then is equal to 5 amps. So in this case, we want to know what? Part A, we want to know what is the current density. So what is this guy? Part B, we then want to know what's the drift velocity. We want to know that. And then finally, part C, we want to know what is the RMS velocity if this thing has a temperature of 20 degrees Celsius.
What's the RMS velocity?
I'll remind you when we get there. But remember, RMS velocity is when you have an ideal gas. So if I came in this room, what happened then is that the average velocity of the gas in this room would be 0. Because I have as much gas moving in this direction as I'm moving in this direction, as I'm moving in this direction, every possible direction, as long as there's no breeze in the room. So the RMS velocity then is what's known as the root mean squared, which is the average of the square velocity that this thing has. So instead of looking at just the velocity, because those guys are equal and opposite, look at the square of the velocity. So that's what we call the RMS value. We'll play more with a lot more RMS values later, but it's just what it's called, the root mean squared. So great. So let's talk about the current density. So what do we know? So how would we do part A? So if I want to know the current density based off the information that I know, what can I use? Well, before the other.
We can just use I over A.
Good. So in this case, we're going to use that the magnitude of the current density is equal to the current divided by the cross-sectional area. Good. Now in this case, what's my cross-sectional area? So it's a wire, so it's a cylinder. Good. So this is then going to be I divided by pi r squared. But again, I'm given the diameter. You know, the radius is equal to half of our diameter, which means the radius squared then is going to be the diameter squared divided by 4. So finally, I can write this as 4 times the current divided by pi d squared. Look at my numbers. What I find in this case then is that my current density is 6.2 times 10 to the 5th amps per meter squared. My current density. Okay.
Where did 4 come from?
The 4 came from because I'm dividing by the r squared here, so this would be a d squared over r squared, or over 4 squared, 2 squared over 4, which would give me a 1 over 1 over, which then means that moves to the top. So that's where the 4 comes from. Okay. Part B then says, okay, well, what is now the drift velocity? Well, we now know that the magnitude of the current density is simply equal to the charge of the charge carriers times the number density times the drift velocity. So in this case, I would then say, well, my drift velocity is then simply equal to the current density divided by the charge of the charge carrier, which in this case is an electron. So we just put an E there, times then the number density. So this is my drift velocity. So what's my number density? So my number density then is, since this is copper, we would then look up what that guy is. Let me find it here. So my current density. And I write it down. Okay. Well, again, we were just looking up I'll tell you what it is next time. Sorry, I forgot to write it down. So this works out to be about 0.05 millimeters per second. Sorry about that. Please stay off the right. So what does this say? So this says that under this particular wire, where I have a current of 5 amps and I have a diameter, the average velocity that the electrons are moving through this is about 0.05 millimeters per second. That is slow. It's really slow. Okay? So of course that always begs a question that if I turn off the lights in here and I turn it back on, so usually I have them faster now, this thing's a little delayed, but instantaneously the light would turn on as soon as I flick my switch. But what this thing is saying that is if I have this copper wire, my electrons are only moving at 0.05 millimeters, which means that what? If this was about a meter from the light switch to the closest light, it would take about 5 hours for the electron to move from this location all the way into the light. 5 hours it would take one single electron to move from that light switch all the way through 1 meter worth of wire. So the question is, how come I can turn this thing on instantaneously if it takes 5 hours for the electron here to go all the way through the wire to get it to that particular point?
Depending on one electron, it's all of the electrons.
Exactly. So what's happening is, again, I have electrons all the way distributed throughout this entire wire because it's copper wire. So when I flick it on, that one single electron that's about ready to fall in is what causes it to move on first. Exactly. So all the electrons are moving, again, at a slight speed of 0.05 millimeters per second, which again is really slow. But again, this thing instantaneously turns on because, as Tim was saying, the entire wire is full of electrons. So each one of these electrons is moving on average with that particular velocity. Now let's compare this to the RMS velocity. So let's go back to 205. So we know from physics 205, the RMS velocity, which is equal to the root mean squared. So this is equal to the square of the average velocity squared, or sorry, the square root of the average velocity squared. This thing was equal to the square root of 3 times Boltzmann's constant times the temperature in Kelvin divided by the mass. So this temperature here is in Kelvin. So in this case, we're given the temperature in Celsius, which was 20, then to turn it into Kelvin, we said add 273.15. This in this case is what the mass of an electron. So in this case, this is going to be the mass of the electron, where the mass of the electron is 9.11 times 10 to the minus 31 kilograms. And we have Boltzmann constant, so we plug in all these numbers. What we find is that the RMS velocity is actually 1.2 times 10 to the 5th meters per second. So what does this thing say? What this thing says is that if we look at the electrons inside of this wire, let me go back to my wire here. What's actually happening is this thing is full of electrons, but each one of these electrons is moving around in some random direction, which is the RMS velocity, which is about 1.2 times 10 to the 5th meters per second. So this thing is flying around in all kinds of different weird directions. Each one is moving in some sort of strange direction. Now, when I apply my potential difference across this to create the current, what happens then is that this section, which has RMS velocity of each one moving around in a different direction, this section here of electrons will then slowly be pushed down the length of this wire at an average rate of 0.05 millimeters per second. So what's actually happening is this acts just like an ideal gas, where each one of these guys is zooming around, but then when I apply my potential, a block of this thing as it's zipping around in different directions is then going to slowly migrate its way down the length of the wire at a very, very slow rate of 0.05 millimeters per second. So this is actually what's physically happening inside of the wire. So if I want to think about it, this block of electrons here is then slowly moving down in this direction with our velocity. So every block of these electrons slowly being pushed down, but again, the overall viewpoint of the electrons on the inside is they're acting just like an ideal gas, zooming around in different directions at a much higher rate than this propagation down due to this potential difference. Okay with this? a much better picture of what the electrons are actually doing. Seem to be so enthused by that. Okay, everybody's okay? So good. So as I said earlier, it turns out that the current density is actually directly related to the electric field. So now what I want to know is what is the relationship between the current density and the electric field. So what is the relationship between these guys? Now, to do this, we're going to go back to Ohm's law. So remember, Ohm's law says that the potential is equal to the current times the resistance. Now, what we know is as long as this thing has a constant electric field, so let's pretend we have a constant electric field. In this case, I can rewrite the left-hand side as simply going to be equal to the electric field times the distance d. Remember that the electric field is equal to the volts per meter, so that means my voltage is the same thing as the electric field times. We now know current is the same thing as what? The current density times the area. So here I'm going to assume, and again, my current density is also equal to a constant. And then we also know that resistance is the same thing as resistivity times the length divided by the cross-sectional area. Now, this length here is actually the same thing as the distance d, which means I'm going to simply write that as the distance d. Okay, so those two guys are actually exactly the same. So what happens then is that this area cancels this area, this distance d cancels this distance d, which means that I get the electric field then is actually equal to the resistivity times the current density. So this is actually the relationship between the two. Customarily though, we're typically going to write this more as the current density is equal to 1 over the resistivity times the electric field. Remember, as we defined yesterday, 1 over the resistivity is the same thing as the conductivity. So it's actually going to be the conductivity times the electric field.
Is that symbol?
That's a sigma, lowercase sigma. So this is what we call the microscopic version of Ohm's law. Microscopic version of Ohm's law. So again, microscopic version of Ohm's law simply says that the electric field is related to the current density, but again, since this guy is always positive, or this guy is always positive, these two have to point in exactly the same direction. So whatever the direction is established by the battery in the direction of the electric field, that's not going to be the direction of the current density. They're related by simply the resistivity or, again, the conductivity. These two things are exactly the same. Well, inversely the same. Okay? Let's do another example. Good. So this says we have a 115 volts power supply battery is applied across a wire that is 10 meters long and has a radius of 0.3 millimeters. And then it says the magnitude of the current density is 1.4 times 10 to the fourth amps per meter squared. What then is the resistivity of the wire? So let's write all these things down. So our example. So we have a radius which is 0.3 millimeters. We have here potential which is 150 volts. Good. We have a length which was equal to 10 meters. And we have finally the magnitude of the current density is then equal to 1.4 times 10 to the fourth amps per meter squared. So from this, what we want to know is what's the resistivity? Well, we now know that what? From the microscopic version of Ohm's law, we know that the electric field is equal to the resistivity times the current density. What else do we know? We know the electric field is the same thing as the potential per unit length, which is then equal to the resistivity times the current density. What's up, Homer?
Is there a reason why we use the microscopic version and not the other version?
Oh, the other version,
Like the equals ion?
you mean in something like this?
Yeah.
I mean, we would get to the same answer, as long as we use R as rho L over A, so we would get the same answer at the end of the day. So we could use that, yeah. But we have a new toy, so let's use it. Basically. So in this case, what this says then is that the resistivity is simply going to be what the potential divided by the current density divided by the length. So from here, we get resistivity then is going to be equal to the potential divided by the current density times the length. So it's going to be 115 divided by 1.4 times 10 to the fourth times then 10 meters. So this tells me that now my resistivity is going to be 8.2 times 10 to the minus fourth ohm meters. So this is my resistivity. Okay. So finally, the last thing to talk about is, again, let's go back to our beautiful mental picture. So what we said is the battery is here to supply a potential difference, which supplies an electric field, which then accelerates the charged particles, which then go into this electrical element. These guys try to accelerate them across this electrical element, but again, the electrical element has atoms in it, which means they're going to make elastic collisions, which means they're going to part some of their kinetic energy then onto the atoms themselves. The atoms then are going to vibrate much, much faster, which means as their kinetic energy increases, their temperature increases, which means that they have power delivered to them. But by conservation of energy, that power which is delivered to them is also the power that they're going to lose via thermal energy. So what I want to know then is how much power is being lost due to thermal energy. So this is the last thing we need to talk about. So what is the power lost due to thermal radiation? That's what I want to know. So good. So what I know then is what? Let's say here is my electrical element. What I know here is that I'm going to have some point over here B. I'm going to have some point over here A. And what I know then is that the potential difference between B and A. So BAB is then going to be equal to some positive. So in this case, it's simply going to be equal to I times R. Which basically means that what? If I had an electric field, which is pointing in this direction, what that means then is that the potential at A is greater than the potential at B. Now, what's happening though is that the battery is supplying power to this thing, which means that there's a potential difference across this guy. Let's say this is my potential difference of B. Now, what I'm going to do is I'm going to move a charged particle from A to B in this direction. So in this case, let's say here's my charged particle. Sitting here, I'm going to call that charged particle a little tiny amount of charged particle dq. And what I want to know then is how much work is done to move that charged particle across this potential region of B. So how much work is being done? In this case, by the electric field. So how much work is being done by the electric field, i.e. how much work is being done by the battery. So how much work is being applied to this? Good. So we know that, remember, that work is equal to the change in potential energy, which is then equal to the charge times the change in potential. Now in this case, this is going to be then equal to the potential, which we know is a constant V, times the amount of charge dq that I'm moving across my wire. Which means then that this is also equal then to the change in potential energy. So what's happening then is my charged particle here, the dq, has a change in potential energy going from this point to this point, where it's moving from high potential down to low potential. Now, if this happens over a time frame of then say delta dt, we can then say that what the power, which is then equal to the rate at which the energy is changing, is then going to be equal then to what? The potential times the change in charge divided by the change in time. Well, what's the change in charge per change in time? What do we call that yesterday?
That J.
A J, or J, it's related to J. Change the charge for J.
Oh, I.
That's I, it's just current, right?
Current.
So this is simply equal to the potential times the current. So what this thing says then is that the power delivered by the battery, or in this case, by the electric field to my electrical elements is simply going to be equal to the potential times the current. So this is the power which is being delivered. Now, conservation of energy then says that the power delivered must also be equal to the power which is lost by this electrical element. Which means that my power which is being lost is then going to be equal to simply the potential times the currents. So this is why, for example, when you turn on your range on your stove, the heating element turns red. This is why. So what you're doing is you're applying a power to it, you're delivering power to it, which is simply the potential times the current, which means as the temperature increases, we then see the color change because the temperature is increased. And remember, we talked about 205 that all different colors correspond to a different temperature. So you see it turning a different color because you're applying more power to it, and simultaneously it's losing that amount of power by conservation of energy. Now, we can also say that using Ohm's law, potential is equal to the current times the resistance. So I can also write this as power loss is equal to what? The current squared times the resistance. Or I can write the current then as equal to the potential divided by the resistance, which means I can also write this then as the potential squared divided by the resistance. All of these are exactly the same thing. So the power which is being lost by any electrical element is simply equal to the potential times the current. But if I'm specifically talking about a resistor, in this case, then these are then two identical ways of talking about power loss, which is either the current squared times the resistance or the potential squared divided by the resistance. So these two are specific only to resistors, where this one is specific to any electrical element. So any element. This is true. Right? So this is our power loss. So again, as long as I have current running through a wire or some sort of resistor, I have energy being lost, and that energy is being lost due to the increased kinetic energy of the atoms inside of the resistor oscillating, which means the temperature increases. As the temperature increases, again, I'm radiating away all of this energy in the form of thermal energy. So most of it's going to be thermal energy and as well as some just radiation, which is given off, i.e. the light. So that's where basically most of the energy is going to come from. But mostly it's just going to be lost in thermal energy. So good. So let's use this. Let's do an example. So before we start our example, does anybody know why you have a circuit breaker in your house? Or in your dorm room?
Something draw too much current.
Good, and what would happen if you draw too much current?
Burn up the wires.
And your house, right? If it gets way too hot, right? So this is actually the reason why you actually have a circuit breaker. The point of a circuit breaker is that every gauge of wire, where gauge talks about just the diameter of the wire, means it can withstand a certain amount of current running through it before it gets too hot. So the circuit breaker there is to say, okay, if you have a certain gauge wire, say a 12 gauge wire, that can withstand, say, I don't know, 10 amps worth of current. So what it does is it measures the amount of current running through that particular wire, and if it exceeds 10 amps, it's going to say, well, this thing's going to get too hot, where I can either burn out the wire, or I can actually burn out my entire house. So if it measures using an ammeter that this thing has increased higher to 10 amps, it'll kill the circuit, ensuring that you actually don't burn down your entire house, which would be a good thing. So, okay, so let's use that. Let's do an example. So this says that there's much variability in a lightning bolt, but a typical event can transfer 10 to the 9th joules of energy across a potential difference of 5 times 10 to the 7th volts during a time interval of about 0.2 seconds. So from here, we want to estimate the total amount of charge transferred between the cloud and the ground. And then finally, the current in the lightning and the average power delivered in 0.2 seconds. So let's draw our scenario. So here is my cloud. Here then is the Earth. So what happens here? So basically what happens is the Earth acts as a gigantic reservoir of negative charge. So the Earth itself is going to become negatively charged. This is the reason why you run wires into the ground, the Earth, because it acts as a huge reservoir of negative charges. So if you get too many charges, you can run them off into the Earth, or if you don't have enough charges, you can pull them out of the Earth to then run your circuit. Now, simultaneously, the cloud becomes charged. So if the Earth is negatively charged, what happens then is I'm going to get positive charges then in the cloud here. And this thing is effectively going to act like a parallel plate capacitor. Okay. So what happens then is my parallel plate capacitor is going to have a potential difference between them, where in this case, we're told their potential difference then is equal to 5 times 10 to the 7th volts. Okay. Now, once this happens, what happens then is you have now effectively reached the breakdown potential of the air then between the Earth and the cloud, which means you're going to ionize the air. When you ionize the air, you're then going to discharge your capacitor by stripping electrons from the Earth and pulling them up to the clouds. Are we okay with this? So actually, lightning strikes from the ground up, not from the cloud down. Right? So effectively what's going to happen is you're going to pull negative charges upward to then kill this particular parallel plate capacitor. So you're going to ionize the air, and as you ionize the air, that's what's going to create our lightning bolts. So what do I know? So I know then that the energy, the potential energy which is transferred, is going to be 10 to the 9th joules, and this happens over a time frame of delta t, which is then equal to 0.2 seconds. So first thing I want to know then in part A is, what's the total amount of charge? So how much charge then is pulled from the Earth to put it into the cloud? This is what I want to know. Okay. We'll do this. We know that's what the change of potential energy is equal to the charge times the change of potential, which in this case is going to be equal to the charge times that potential difference between the ground and the cloud. Which means my charge then is going to be equal to my change of potential energy, which in this case is called potential energy, divided by my potential. So it's going to be then equal to 10 to the 9th joules divided by 5 times 10 to the 7th volts, which then is equal to 20 coulombs. So I have 20 coulombs with the charge, which is ripped out of the Earth and then brought up into the cloud. Okay? Part B then says the current in the bolt. So part B, we want to know what's the current. Well, we know the current is simply equal to the change in charge divided by the change in time, which in this case is the total charge divided by the change in time. So here I had 20 coulombs with the charge divided by 0.2 seconds, which means I have 100 amps with the current. And as we previously discussed, 100 amps of current is enough to kill a person. So if you're struck by lightning, odds are you're going to die. Finally, the last part then says, what is the average power delivered in this 2 seconds? Good. So for part C, we now want to know what is the average power delivered. Well, we now know the average power is simply equal to the potential times the current, which means in this case we can write this as what the potential, which is 5 times 10 to the 7th times the current, which is 100 amps, which is then 5 times 10 to the 9th watts, which is the same thing as 5 gigawatts. Have you ever seen the original Back to the Future? Remember Doc Brown's running around saying, how much was it?
1.21.
1.21. The 1.21 gigawatts is what he called it, but it's actually gigawatts worth of power, right? This is why they use light, because there's way enough more energy than 1.21 gigawatts contained inside of a lightning bolt. So this is why they actually had to catch the lightning, be able to run the DeLorean to go back in time. I got one more example, but we're out of time because I was just talking too much. So anyways, we'll do that one on Monday, and then we'll be done with this chapter. So basically, as of right now, you can actually do everything in this chapter. You do everything effectively in chapter 26 and 27, which means that Monday we'll finish up the last problem and we'll start chapter 28. 28 is where we start doing our circuit analysis. At least I didn't fall asleep while talking.
Wait, is there text?
You were late. I only had a half hour sleep left. So that didn't make any sense today.
What were you doing?
Couldn't sleep. Had a hockey game last night. It was all too wound up, I guess. And